Hello, we are Shelley Compendio and Andrew Kim, and our replication project is based on the paper Temporal Relation Ranking for Stock Prediction. So before we go into the replication project, we're just going to go over some background information about the paper. The paper addresses the problem of stock prediction. Predicting the future trends of a stock is important because it helps investors make informed investment decisions. There are some deep learning solutions that exist out there, but the authors state that these solutions are ineffective because they treat stocks as independent of each other. Stocks can be related to each other if they come from companies that are in the same sector. Stocks can also be related to each other if they have a supply-consumer relationship or if one company is a parent of the other. And we'll also go into more detail about what it means for two stocks to be related later on in the presentation. Since there are problems with existing deep learning solutions, the authors have proposed a new deep learning solution called Relational Stock Ranking, or RSR. RSR formulates stock prediction as a ranking task and ranks stocks based on metrics such as return ratio. Some advantages to RSR are that it tailors to the deep learning models for stock ranking, and it also captures stock relations in a time-sensitive manner, which is very important for the problem statement. The most important part of RSR is the temporal graph convolution, or the TGC component. This component models temporal evolution and relation network of stocks. So in a minute, we're going to see how this TGC component fits with the RSR framework. But before we do that, we're just going to describe what it means for two stocks to be related. So as I mentioned before, the first type of relation that the RSR model takes into account is sector-industry relations. Stocks that are under the same industry are similarly influenced by the prospect of the industry. The authors used the New York Stock Exchange and NASDAQ data for their experiment, and this data that they obtained was organized into a hierarchy structure that can be seen in the top right figure of this slide. Sector-industry relations are detailed in the sectorindustry.py file, which we will go over and explain later on in the presentation. So the second type of relation that the RSR model takes into account is wiki company-based relations. So for this, first order and second order company relations were extracted from the knowledge base Wikidata. A company like Google has a first order relationship with a company like Alphabet Inc. if there's a statement in Wikidata that has Google as the subject and Alphabet as the object. A company like Boeing has a second order relationship with a company like United Airlines if there's a statement in Wikidata saying that they share the same object, such as Boeing 747. So now we're going to go over what the RSR model looks like. First, historical time series data is fed into the long short-term memory or LSTM network as shown in the bottom of the figure. This step captures sequential dependencies and stock-wise embeddings. Next, the data passes through the TGC component that we talked about before. This step revises the sequential embeddings by taking relations into account, and this is also done in a time-sensitive manner, which again is pretty important for the problem statement. Finally, the sequential embeddings and relational embeddings are concatenated together and fed into the fully connected layer that you can see at the top of the figure on the slide. This obtains the final ranking score of stocks. So, as mentioned before, the authors conducted an experiment on the New York Stock Exchange and NASDAQ data using two models. The first model that the authors used on this experiment was used to study the effectiveness of stock ranking formulation. They ran the rank LSTM model similar to RSR, but this has no TGC layer. Since the rank LSTM model doesn't have a TGC layer, it doesn't take the relations between stocks into account. So we can see on the top right figure that this model performed better than other methods with no ranking formulation. However, rank LSTM was inconsistent and it performed worse on New York Stock Exchange data. The second model the authors used in their experiment is a regular RSR model, which is the one that they were proposing in the paper. They ran this RSR model, and the point of the experiment was to study the impact of stock relations. We can see on the bottom right of the figure on the slide that this model performed better than other models with no relation, so this verified the effectiveness of the TGC component. Overall, the authors found that taking stock relations into account was helpful for stock ranking, and that the TGC component that they are proposing in their paper was a promising solution for encoding stock relations. So after running these experiments with the two different models that we discussed, the authors of the paper evaluated them using backtesting strategies. They had 3 strategies: top 1, top 5, and top 10, buying stocks with the top 1, 5, 10 highest expected revenue, respectively. So, for example, for the top 10 backtesting strategy, the authors split up their budget to trade the top 10 ranked stocks on each testing day. It was found that the RSR model did not meet the expected performance under the NASDAQ industry setting. So this indicates that the industry relations are less effective on the NASDAQ dataset. Overall, the performance for IRR, which was the metric that they were using to measure the effectiveness of the model, was top 1, then top 5, and top 10. So top 1 was the most effective, and top 10 was the least effective. The reason for this could be that the ranking algorithm could accurately rank the relative order of stocks regarding future return ratios. Once the order is accurate, buying and selling stock with higher expected profit would achieve higher cumulative return ratio. So that was just a little bit about some background information about the paper that we read for this project. Now we're going to dive into what we did for the replication project.
So one of the first things we had to do was select our data set. We ended up going with data set 1, which was the historical stock prices data, because this was the only data set that dealt with actual stock prices. And this was kind of important because our model, it was using these stock prices to predict the return ratio from day to day. The data that we were given is only minute data, and we needed end of day data. So we did have to add this function here called data reformatter. What it basically did is it kind of sifted through the minute data that we got, and then for a certain time period, the start date, end date, if you look into the code here, that kind of represented the market open, market close for a certain trading day. And then within this time period, we would figure out the mix, the min, the open, the close of the stock, and then we would add all the volume measures so that we could kind of rectify this into one like stock bar, which would represent this end of day data. And then in this reformatted data part right here, this is making sure that we kind of organize the data so that it's the most similar to how the data that the authors used in the original paper, so that we could really easily just kind of feed this data into their existing functions and files, so that we don't have to modify too many of their functions that are already written in the repository. The next thing that we had to do is restrict the stock universe. In the paper, they use kind of around like 2,000 stocks, in total between the New York Stock Exchange and NASDAQ. And the data that we got, it's only about like 100 stocks, maybe. No, I don't even think it's that many. And they use this stock universe. They keep it in a file, and they use this stock universe file in other places, such as like in the sector industry.py file, where they kind of map the industry relations. They read from the CSV file to figure out what stock relations they need to find. It's kind of meaningless if we have, one stock that we do have in our data file with a relationship with a stock that's not in our data set file. So we didn't want any of that. So we had to kind of restrict the stock universe. And this top part of the code, this is us kind of writing the tickers or the stocks that we're actually going to be using to a CSV file, which we could reference later. And then down here, this is actually in the model file. This is us kind of restricting some of the data to be only the stocks that we used. So in this like for function or for loop, we have this np.where. So the ticker has to equal a ticker in our list. Otherwise, we just kind of toss it out because we don't want the data. So once we modified all the files, all the metadata, we could pretty easily feed these files into the existing functions that the authors of the repository had written already. And yeah, because we had kind of modified the data to be what these functions expect, the reading in of these files was pretty frictionless, which is why there's not much code on this slide, or not any code on this slide. So yeah, we just ran the end of day file, and this generated a file that the model would use to reference for the end of day prices. We ran these two files, sector industry and Wikidata, and these generated the relational data that the model would also use for its special layer, which kind of map the relationships between stocks. And then we wrote these files into certain folders. The end of day data into the test features folder, and then the relational data in the relation folder. And then we edited the model file so that it would read these files that we generated directly from where they got generated. So yeah, we read the files into relational rank LSTM, which is the subject of the paper that we read. It's the special layer, special part of the model that kind of maps a temporally dynamic relationship between stocks. So that's kind of in this code section up here is just kind of reading in the data. Down here as well is just kind of reading in the data that we created with the preprocessed files that I mentioned earlier. And then so in the paper they actually split the data between New York Stock Exchange listed stocks and NASDAQ listed stocks. So to kind of keep it as frictionless as possible, we also just ended up splitting our data into NYSE and NASDAQ, so that we could kind of read our files a lot easier. So we did this, and then we used the recommended settings that they gave in their own repository README, and this gave us the output of the model trained on the data that we provided. So now I will go into some problems that we ran into while we were feeding our data into the existing code files. So one issue that we ran into was the sheer size of the data set that we were given. The authors actually use end of day data because that's what their model expects. So the amount of data points is actually way less than the minute data that we're given, because we have a data point for each minute of each day. So there's exponentially more data points that we have to work with. So in the code that they provided, they actually first read all of the file data into this one giant array. It's like an end of day array, and it may have worked for them, but when we tried to run it, we ran into memory issues. My machine has 16 gigs of RAM, but it was using up to like 95% of that RAM. So and it ended up not even being able to execute because you see this error right here, because it wasn't enough. There wasn't enough memory to allocate for a certain data set that ended up being like 334 megabytes. So yeah, so we to rectify this, we had to split the datas into fourths. You know, it's a pretty simple solution, but we would just run it in fourths so that the memory that had to be stored in this data, it would end up being a fourth of what it would have to be if we just kind of throw it all in there at once. And this kind of kept the RAM usage to about 60% per loop. So that ended up being way more manageable, and we ended up being able to process the data this way. So one of the other main issues that we ran into was that the code that they provided, it actually only contained the second half of the model. According to the repository README, what you were supposed to do, at least for the code that they provided, is you're supposed to download the output of the first half, and then you feed that output into the code that they provided in the repository. And for whatever reason, they didn't make the first part public. So this kind of became an issue when we're trying to run this model with new data points, because we can't generate new data points from the first half. We can only use the output that they gave us and kind of tailor that to the data that we had. So to solve this, we kind of had to use the intersection of the dates that they used and the dates that we had, and that ended up being about 2 years of data from about 2016, the beginning of and here are the results of running the model with our data set. So this is the results after running the model on the NASDAQ and NYSE data. Looking at the data points, they're pretty similar. The NASDAQ has a little bit lower mean squared error than the New York Stock Exchange stocks, which is interesting because that was actually the opposite of what the paper found. They found that, or at least they found that New York Stock Exchange had lower MSE than NASDAQ, so it's interesting that it's flipped here. But if we do look at the order of kind of all these metrics, it's around the same as the order that the paper listed when they tested with their data. So we know that it worked, and it's pretty accurate. Yep.